This sac104 problem number 7. We got two disks sliding toward each other on a flat frictionless surface. Disk 1 and disk 2. Horizontal frictionless surface. That's 2. It's got mass M2, and this one's got a mass M1. They got the same thickness, diameter. I don't think we're going to need. They collide. The collision is not completely elastic, so I can't assume that E is equal to E prime. But after the disk, 2 is at rest and 1 is moving. So after the collision, I should say. So let's put 2. We've got that V2 prime equals 0 and 1 is moving. I'm going to say leftward with a positive speed V1 prime. How much kinetic energy was transformed? Okay. The fact that it's not completely elastic tells us we can't say that the energy was constant, but momentum is still conserved. There's no outside forces tending to speed either one of them up or slow either one of the other one down. So let's see if I can establish a reference level. So everything's at this reference level, everything's got 0 potential energy before and after with that choice of reference level. And I can say the momentum is conserved. So I'll say the sum of the momenta to the right is equal to the sum of the momenta to the right in the after picture. This was in the before picture. It's equal to it in the after picture. Now, what these arrows with labels mean, you can consider this to be a directed magnitude. That is, this is positive if disk 2 really is moving to the left. In the after picture, this is positive if this really is moving to the left. So when I count the sum of the momenta to the right direction, this one goes in with a positive and this one with a negative. So V2 itself is a positive value, as is V1 prime. So if it's 5 kilogram meters per second, for instance, that means 5 kilogram meters per second leftward, because it's called leftward positive by means of this arrow. So I'm going to go M1 V1, that's to the right, and then minus M2 V2, because this is positive leftward, and that's equal to minus M1 V1 prime. Need to solve that for V1 prime to get the velocity of disk 1 in the after picture. And that's going to be M2 V2 minus M1 V1 all divided by M1. So that's an intermediate result. Alright. Now, at this point, now that I know the velocity of all of them, both before and after, what I can do is calculate the total energy in this picture, calculate the total energy in this picture, and the difference is how much got transformed. So E transformed is just E original minus E final. This is all kinetic energy, but I'm going to go ahead and write down K plus U minus K prime plus U prime, but both of these are 0. Everything's at the reference level before and after, so the E transformed is just K minus K prime. And that's K1 plus K2, kinetic energy of object 1 in the before picture plus kinetic energy of object 2 in the before picture, minus K1 prime plus K2 prime. But we're told that disk 2 is at rest in the after picture, so that's just 0. So this is just K1 plus K2 minus K1 prime. That's 1/2 M1 V1 squared plus 1/2 M2 V2 squared minus, remember, big difference between kinetic energy or energy in general and momentum is momentum has direction associated with it, so I have to worry about which way when I put the algebraic signs in. Kinetic energy has no direction associated with it, so just write down the expression for it with no concern for which way. There is no which way to it. And then 1/2 M1 V1 prime squared. So this would be my answer, except it's got an unknown V1 prime, but that's what I did all that work with conservation of momentum for. By the way, yeah, they do have two separate masses, so it was sensible to use two different symbols for that. 1/2 M2 V2 squared. All that stuff is known. And then minus 1/2 M1. Do the pure substitution here. Just copy this expression. M2 V2 minus M1 V1 all over M1 right here. And then squared. And then I'll check, make sure I copied that right. Okay. Looks good to me. And that's the answer. I'm thinking it's not going to simplify very much, so I think I might just leave it just like that. I'm going to have another positive 1/2 M1 V1 squared, so that would add on to that one, and then I'll have a minus 1/2 M2 over M1 times V2 all squared, so it's a piece that looks something like that. I guess it's polite to gather all the... No, I'm going to have mixed terms as well, so I don't know that it gets any simpler than this. That would be a matter of opinion. Could factor a 1/2 M out if we wanted, but I think I'll leave it just like that. So it's not obvious that if I expanded this out and combined terms that the expression would get simpler. Factor in the 1/2, well then I get more parentheses involved, so I think it's a matter of opinion on whether or not that can be simplified. I'm going to leave it just like that. So the amount of energy that got transformed is this expression right here. I should probably point out one thing. We solved this problem using conservation momentum as an intermediate step to get V1 prime. Normally you can't get V1 prime or V2 prime just from the conservation of momentum because you get one equation and two unknowns. The reason we could in this case is because one of them was actually given. V2 prime was given as 0, so that left us with only one unknown, so it was possible to get an actual expression for that one unknown, and if we had values we could plug them in here and get an actual value for that V1 prime, the one unknown. But here's my final answer for the amount of energy transformed during the collision. I guess I should do one more thing and make sure I answer the question. How much of the kinetic energy of translation that we had was transformed into other forms as a result of the collision? And that's exactly what we have found.